Hi guys, welcome to the week 9 problem class for Introduction to Astrophysics. Let's start. The first exercise is about gravitational lensing, which is the phenomenon for which an object of mass m called lens, which is posed between a distant light source and an observer, bends the light from the source as it travels towards the observer. The consequence of this is that if you use a telescope, you will get an image of the source which doesn't represent the true position of the source in the sky. We will need this geometrical sketch to solve the exercise, so it's better if we define the quantities now. Here we have the distance between the observer and the lens, which is called DOL. DLS is the distance between the lens and the source, and the sum of those two, which is the distance between the observer and the source, is called DOS. We have also other relevant quantities like B, which is called impact parameter, and then we have the distance between the source and the image, which is called H, and then we have this A here, which is the difference between H and B. So A plus B is equal to H. Then we have these angles here. We have alpha, which is called deflection angle, theta E, which is called Einstein angle, and gamma is the difference between those two. So the first question is, given the deflection angle that you can compute using general relativity, and using the geometry of the diagram for which small angle approximations are valid, show that Einstein's angle is given by the following relation. Let's start. Again, we have to look at the figure. From this, we can realize that theta E, in particular the tangent of theta E, can be expressed as a chain of relations. In fact, we can see that the tangent of this angle can be expressed as the ratio between B and DOL from this triangle. But we also have this other triangle, so we can define it as A over DLS, but also we can define it as H over DOS. And this leads to this first chain of equalities. Since small angle approximations are valid, the tangent of theta E can be approximated with the angle itself. We can do a similar reasoning for the angle gamma, which, again, from the triangle, we can define it as the ratio between B and DLS. Now, again, using a small angle approximation, the tangent can be approximated by the angle itself. Now, since we saw before that the deflection angle is the sum of the Einstein's angle plus gamma, and H is the sum of A plus B, we can write alpha as A over DLS plus B over DLS. Then A plus B is H, so we have this equality here. And then, using the relation we saw in the previous slide, we can say that we saw that H is approximately theta E times DOS. So we plug in this one, and we get that theta E DOS over DLS is approximately alpha. And this is the first relation we are going to use. Now, the question gives us a relation for the deflection angle, which is 4gm over bc squared. Now we can put this relation here in the left hand side of this other relation, and we get this approximately equality. So we can also use the fact that B can be expressed as theta E times DOL. We can rearrange for theta E, and we get theta E squared equal to 4gm over c squared, DLS over DOL DOS. you can see that just by taking the square root of this relation, we get the result that the question asked. So the first point is solved. Now, the second part of the question says, for the case where a galaxy cluster of mass m is located exactly halfway between the light source, another galaxy in this case, and the observer on the Earth, an Einstein ring is observed with theta e 0.5 arc minutes. The distance to the cluster is 1 gigaparsec. What is the cluster's mass m? So, before going to the solution, let me say that the Einstein ring is basically a ring in angular coordinates. So, this theta e is basically the radius of this Einstein ring. Moreover, the first thing we have to do is to convert the data that we are given here to SI units. So, to convert arc minutes to radians, we have to multiply the data we are given by 60 arc minutes degrees to the -1 and this to the -1. Once we convert it into degrees, we can go from degrees to radians using the usual proportionality factor for degrees and radians. And the result is 1.45 times 10 to the -4 radians. Then we have also to convert gigaparsec to meters, remembering that 1 gigaparsec is 10 to the 9 parsec, and the conversion factor is this one, 3.09 times 10 to the 16 meters parsec to the -1. And we get that DOL, in this case, which is the distance between the observer and the lens, which is given by the question, is 309 times 10 to the 25 meters. Now, to solve the exercise, we can use the relation we derived in the previous part of the question and rearrange in order to get m. So, this is the formula we are going to use. Then, since the lens is halfway through, as the question says, we also have this equality here, that the distance between the observer and the lens is equal to the distance lens source. So the sum of those, the distance observer source, is equal to 2 DOL. If we plug in this formula here for m, we get that m is equal to theta e squared, c squared over 4g times 2 DOL. If we plug in the numbers converted as we did in the previous slide, we get 4.4 times 10 to the 44 kilograms, which converted in solar mass units is 2.2 times 10 to the 14 solar masses, where we used, of course, that c is 3 times 10 to the 8 meters per second and g is 6.67 times 10 to the -11 kilograms to the -1 meters seconds. Now we can step on exercise 2, which is about the velocity dispersion of galaxies. The question is, calculate the velocity dispersion for a galaxy cluster using the measurement of the radial velocity for 5 of the contained galaxies in the cluster, which are the ones given here. The velocities are given in the question using kilometers per second. For simplicity, I converted this in megameters per second, just for shortness. So the solution is that the velocity dispersion squared, dubbed sigma squared, is given by sigma squared equals 1 over n, where n is the number of galaxies in your catalog, sum over the galaxies of the single velocity of the velocity of the single galaxies minus v mean, which is the mean velocity of the galaxies, squared. So before applying this formula, we have to recognize n and v mean. In our case, n is equal to 5 and v mean is the mean velocity of the galaxies, and we have to compute them. So the formula for v mean is basically the sum over all the velocities that you have over the number of the galaxies. So is 1 over 5 in our case, and just sum the velocities that we are given in the data. And what we get is 6.7 megameters per second. Now we can apply the formula we saw in the previous slide to compute sigma squared. And this is the formula you should get when you plug in the numbers. So what we get is 1.7 over 5 megameter squared per second squared, which is 0.34 megameter squared seconds per second squared. And now we have to convert this into meters. So since 1 megameter is 10 to the 6 meters, we have a squared, so the conversion factor is 1 times 10 to the 12. That's how you get the last passage for the right hand side. Consequently, the velocity dispersion, which is the square root of what we got, is 5.8 times 10 to the 5th meters per second. Last question of the problem class, which is, we are given the radius r of the galaxy cluster, which is 0.5 megaparsec. Calculate the total mass of the cluster. We know from the lectures that the mass of the cluster is given by this relation, m equal 4 sigma squared r over g, and we have just to apply this formula. But before applying the formula, we have to convert everything in SI units. So the first thing is to convert megaparsecs to meters, remembering that megaparsecs is 10 to the 6 parsecs. So what we do is just multiply what we are given in the question by 10 to the 6 parsec, and then we multiply by the conversion factor we also saw before. And we get 1.5 times 10 to the 22 meters. Finally, we can apply the formula, and what we get is 2.3 times 10 to the 44 kilograms, which can be converted in solar masses just by dividing this value for the mass of the sun in solar masses, which is roughly 2 times 10 to the 30 kilograms. And what we got in the end is 1.2 times 10 to the 14 solar masses. And this is the last thing we are going to do in the problem class. Thank you.